Hello, Algebra 2. Hope you guys are having a fantastic day. We're just going to move on to 4.5. So 4.5 is about solving exponential and logarithmic equations. And there's like two different ways to solve them. The first way that we're going to learn, which is the method of relating bases, the one that's highlighted here. This is easy if you have the right setup. If you don't have the right setup, then it's kind of easier to do the other way. Because the other way works in like every scenario, and this one only works in some instances, in some types of problems. So I'm going to show you both, and you can kind of, part of the challenge is like figuring out which method to use and when one works better than the other, and but it just kind of like comes with practice. So you'll get better at it. Don't worry about it. You'll get better. Okay, so the first method is the method of relating bases, and basically all that it says is that if you have something like b to the u equals b to the v, right, where b and b are the same base, so you've got like 3 to something equals 3 to something else, and it's the only thing you have left in the equation, then hopefully this is obvious, like the exponents have to be equal. Like, for example, if I have like 3 to the x equals 3 to the 7th, then like x has to equal 7 because you have no other option. Your exponents have to be equal if your bases are equal. Okay? So, cool. Okay, similarly, if you have one log equaling another log and they're of the same base, and you have nothing else in the equation to worry about, like you have log base b of x equals log base b of y, then x sure as heck better equal y, because if they're not, then they're not equal. Okay? So kind of like it makes sense, right? Like if I have log base, it doesn't matter what base, log base 7 of 21, that equals log base 7 of x, then like x has to equal 7, right? Okay, so x has to equal y. So I don't know, for example, say you have an equality like 15 to the 2x equals 15 to the 22. Since you have the same base and there's nothing else in the equation, then 2x has to equal 22. So x has to be 11. Okay, so obviously they're not going to be this simple, but this is the idea. I have a couple examples for you, and kind of the idea with these is that if you have two things, right, you have an equality, and you have, like, for example, I have the base 2 here. Sorry, that was a horrible circling method. I have base 2 here, and I have base 32 here. So the idea is if you can get them to the same base, then you can solve it easier. So like 32 is 2 times 2 times 2 is 8, times 2 is 16, times 2 is 32. So you can actually write 32 as 2 to the 5th. So then you have an equation that is like 2 to the x plus 2 equals 2 to the 5th, right? Now, since you have the same base, you can just set the exponents equal. So you have x plus 2 equals 5, x has to be 3. Okay, sometimes like the hardest thing about solving these is you're not quite sure what the base, you're not quite sure what the base is supposed to be. So for example, number 2, you have 49 and you have 1/7. And neither of those, like to rewrite 49 as 1 over 7 to a power, or to write 1 over 7 as 49 to a power, that sounds horrible. But if you think of other bases that are maybe a little bit simpler that might help you, you can actually change both of them. So for me, I look at 49 and I'm like, oh, 49 is 7 squared. So I think, oh, can I take 49 and write it as 7 squared? And then is there a way that I can write 1/7 as 7 to a power? And when you figure that out, then you can solve the problem quite a bit easier. So go ahead, try example 2, and even 3, 4, 5, 6. You can try them on your own first. And then I'll take some time explaining the ones that people often get wrong, and I'll have the answers for the rest of them. So for example 2, if you got both to the base of 7, you just have to be careful with like your exponent rules, which is why I told you really have to focus on your exponent rules and make sure that you really understand them, because you have to write 49 as 7 squared. And then you're taking 7 squared and raising that to the x power. So that means you're multiplying those two things. So 2 times x is 7 to the 2x. And the same thing here, 7 to the negative 1 is 1 over 7. You multiply those two exponents together. So that's negative x plus 1. So then you have 7 to a power and 7 to a power, so those have to be equal. You get x is a third. Okay, example 3 is a little more challenging because now you have like 3 terms. And again, you want to get everything in terms of the same base. So for this one, I look at it and I'm like, oh, 3 is a nice number. 9 is 3 squared, so that's nice. And 27 is 3 to the third. So in my brain, it makes sense to do everything in terms of base 3. You could do other bases. It's not wrong. It might be a little bit harder, but not bad. You know, you'll still get the same answer as long as you do all of the math right. So for 3, I wrote 9 as 3 squared, and I wrote 27 as 3 cubed. So I have everything in terms of base 3. And then, sorry, I went over and then down. Sorry, that's confusing. But so I changed everything to base 3, and then I combined the denominator. So 3 squared to the x is 3 raised to the 2x, right, because I multiply exponents in that case. And then I have 3 to the x squared divided by 3 to the 2x. And with division, as long as I have the same base, I can do x squared minus 2x. So this is 3 raised to the x squared minus 2x equals 3 cubed. And then now I have the same base on both sides, and that's all I have. So these exponents, x squared minus 2x and 3, have to be equal. So you bring that down, you make it x squared minus 2x equals 3. This is a quadratic, so you could use the quadratic formula. You could factor if it factors, complete the square, any of those ways to solve, right, from when we did quadratics. This one factors nicely, so I found that x is 3 and x is negative 1. There's the answer to number 4. Again, it's easier if you make 5 the base, but you can also make square root of 5 the base, and then this would be root 5 to the 4th instead of 5 squared. So again, you just want to make sure that everything has the same base. All right, try 5 and 6. Those are with logs, so you need to make sure that you get 1 log equals another log, and they're of the same base. So the challenge with the first one is that you have log base 2 of 3x minus 1. This minus 1 is not in a log, and so you're going to have to figure out how to get that into a log. So the trick with this one is that 1 is equal to log base 2 of 2. So I just rewrote it as log base 2 of 2. So, and then I used the quotient rule because this is subtraction. So this is log base 2 of 3x over 2. And now I have a log equals a log with the same base. So the stuff inside here and that stuff should be equal. So you get x equals 10 thirds. And this is the solution to number 6. Okay, so the other way of solving is a little more straightforward because, I don't know, I feel like you don't have to think as much for these kinds because you don't have to like manipulate stuff. I like the other ones better because you can use your brain. These, it's more like using your calculator more often. I don't know, the majority of the problem is using your calculator. Anyways, so what you can do is you can take the log of both sides or exponent both sides. Basically what I mean by that is you can roll the log to just, to change it. When I say take the log of both sides, it's like when you take the square root of both sides. If you have an equation that's like 4 squared, oh wait, no, how about x squared? That makes more sense. Like x squared equals 10 or something. You would because it's an equation, you can do the same thing to both sides. So I can take the square root of one side and take the square root of the other, and I get x equals plus or minus root 10. Okay, so it's the same thing here, except we're taking the log of both sides, not the square root. Remember, log is a function. You're not multiplying by a log. You are taking the log of both sides of the equation, just like you're not multiplying by the square root. Someone will say, can I multiply both sides by log? No, you cannot. Like, my next question will be, can you multiply both sides by the square root? That doesn't make any sense. Like, you wouldn't multiply both sides by the square root. You take the square root of both sides. It's a function, not a number. Okay, so for example, number 7, we have 4 to the x equals 12. Clearly, 12 is not 2 to a power. It's not 4 to a power. So this is not a question of relating the bases, because you can't get 12 to be 4 to a power. It's just not that simple. So what I can do is I can take the log of both sides. The nice thing about this is I get to choose which log I use. I can use log base 4, I can use the natural log, I can use the common log, whatever I want to do. However, these problems you'll probably be getting a decimal answer. And so what I would recommend is using the natural log or the common log, because you have those as buttons on your calculator. So I'm going to take the natural log of both sides because I like the natural log. So now I have natural log of 4 to the x equals the natural log of 12. Now I can use the power rule because it's inside a log, and that x can come out. So I have x times the natural log of 4 equals the natural log of 12. X, so remember that the natural log of 4 is just a number, so it's x times a number. So to get x alone, I can divide both sides by the natural log of 4 and get my final answer. So x is equal to the natural log of 12 over the natural log of 4. Okay, so x equals the natural log of 12 divided by the natural log of 4. So depending on whether I want an exact answer, this is an exact answer, or rounded answer, the decimal, I can get the decimal rounded answer in the calculator. So I do the natural log of 12 divided by the natural log of 4. This is not the same thing as the natural log of 3, or the natural log of 12 divided by 4. Not the same thing. Natural log of 12 divided by the natural log of 4 is 1.7925, approximately. It is important that you do not round until the last step. What I mean by that is, like, don't do the natural log of 12 and then round that and then divide it by rounded natural log of 4. With logs and exponents, those numbers, when you start rounding the decimals, your answers are going to be way, way off. So please don't do that until your final answer. So plug it into the calculator the way I showed you. Okay, so here's example 8. It's a little nasty, but I did log base 10, the common log this time, just to show you that it works with no matter what base you use. So I took log base 10 of both sides. Then I took the exponent out. 2x plus 1 times log of 24 equals log of 9. Log of 24 is just a number. This is multiplication, so we have to divide by log of 24. So I get 2x plus 1 equals log of 9 over log of 24. Subtract 1 to the other side, and then divide both sides by 2. So this green answer is the exact answer, and then the purple answer is the rounded answer that you would get if you plugged it into your calculator. Example 7 is more of a rolling of the log type of problem. So you have log base 6 of 2x plus 3 equals 3. So you can actually just roll the log. So 6 to the third equals 2x plus 3, and then solve it that way. So you should get 106.5 or 213 divided by 2. Okay, example 8 is a little bit more challenging because now you have 2 logs, and you got to combine them into one before you solve it, before you roll the log. But it's not too bad. So this is a product rule, so this is the same thing as the natural log of x times 2, or 2x, and then roll the log. E to the 0 equals 2x, and then just solve. E to the 0 is 1, and then that equals 2x, and x equals a half. And here's example 9. So the only thing that you really have to consider is, like, what do you have to do first? Like, I have to do the power rule, before I use the product rule in this case. Otherwise, I can't combine these two logs. So that's just something to pay attention to, but you get 62.5. Cool.